In this mini lecture, we're going to talk about what BIBO stability really means. So recall that BIBO stands for bounded input, bounded output. So what is BIBO? Well, recall that stability is a system property which only depends on the plant, not the input. In other words, the stability of the system depends on the equations of motion used to describe the evolution of the system over time, or the states, position, and velocity, over time. Hence, understanding the properties of the system transfer function is sufficient for understanding the stability of the system. So in other words, the important take-home message here is that stability is a system property and does not depend on the input. So what does bounded input give us information about the system, or about the stability of the system? So we want to explore that here in this mini lecture. From lecture and from FP section 3.6.1, we saw that if the system, which has a transfer function h of s, which comes from the Laplace of the system h of t, so h of t is the differential operator description of the system, then for stability we needed that the integral from minus infinity to infinity of h of tau, absolute value, d tau, has to be less than infinite. And that meant that the absolute value of h of tau, or really h of t, needs to converge to 0 as t goes to infinity. And this led us to the idea that the system was stable. And if this absolute value converges to 0 as t goes to infinity, then this integral will go to a finite value and we'll have bounded output. So really, you can think of BIBO stability as a way to test. So bounded input, bounded output stability is a test for stability. All right. Another way to say that is it's a necessary condition for stability. So we can look at this since we know using the final value theorem, we know that if h of t has to converge to 0, then h of s also has to converge. And so we can just look at the transfer function when we want to do this. So we don't actually have to look at the solution to the differential equation, which we would need to do here. We can look at the properties of the transfer function. So let me just do a couple of examples of how BIBO stability can work out. So let's see just an example of a BIBO stable system. So we'll use the DC motor transfer function, and that transfer function is given by h of s equals k, and we use the speed transfer function, so this relates the angular rate to the voltage applied. So k over tau s plus 1. And we'll let the input to the system be 1 over s. So that's a step. So that's bounded input. And the question is, what happens to y? Well, y of s, recall, is just h of s times u of s. So if we look at the limit of s times y of s, as s goes to 0, that will equal the limit of y of t as t goes to infinity. Now I'm being a little bit loose with applying the final value theorem because recall the final value theorem does require that y of t as t, taking the limit of y of t as t goes to infinity, that limit exists. And it will have a limit if the system is stable, which would be true depending on the value of tau here, as long as tau is positive. And we're basically saying that, oh, well, the system is BIBO stable if the system is stable, right? And so we're doing this kind of backwards, but again, these are examples of how this would work. So the limit of s times y of s is s times h of s times u of s as s goes to 0, and that's equal to the limit of s times k over tau s plus 1 times 1 over s as s goes to 0, cancel out the s's, let the limit go to 0, let s go to 0, and I end up with k as my output for y. So hence that's bounded output. So this is BIBO stable. We can continue using the same plant, and if we say, all right, well, h of s is still just k over tau s plus 1, but let's let u of s be 1 over s squared. So that's a ramp, and so that is unbounded input. So again, we use the final value theorem, and again, this is not really the proper use of the theorem, but we can verify all this with the time domain solution. So I'm looking at y of s in steady state is the limit of s times k over tau s plus 1 times 1 over s squared as s goes to 0. One of those s's cancels out, and notice as I let s go to 0, I end up with k over 0, and that goes off to infinity. Again, this would suggest unbounded output, but not quite the right application of the final value theorem. So it turns out we can look at the time domain solution using MATLAB and the dsolve command, and we end up with y of t is k times t minus k tau plus k tau e to the minus t over tau. Well, if we look at the limit on this as t goes to infinity, we see that this term goes to 0, this is just a constant, and this term actually goes off to infinity. So in fact, y of t goes to infinity as t goes to infinity, and we verify that we have unbounded output. So even though this system is stable, right, this has poles at minus 1 over tau, and if tau is positive, then that's a stable pole. The system is stable, but if I have an unbounded input to this stable system, I'll get an unbounded output in the transfer function. Well, if you think about what this is, this transfer function represents the speed, and if I say, well, increase the speed, since it's a ramp, so when I linearly increase the speed, then the output will linearly increase the speed. So this makes perfect sense that as I command this to go faster and faster, the motor will go faster and faster, and the angular velocity will just increase with time. So it is, even though the system is stable, for unbounded input, I get unbounded output. We can look at an unbounded input, bounded output example. So just to use some numbers here, let's let h of s equal s over s squared plus s plus 1, and let's let u of s equal 1 over s, 1 over s squared. And then we can look at the limit of s times h of s, u of s, that's equal to the limit, and this is as s goes to 0, of s goes to 0, of s times s over s squared plus s plus 1 times 1 over s squared. Well, notice that this s and that s cancel out with those s's, and I end up with 1. So this is a system that has, this is a ramp input, and this is a, so that's an unbounded input, and we find that we have a bounded output. So in this case, this system is capable of actually accommodating, you might say, accommodating an unbounded input and keeping a bounded output. Notice if I had a bounded input for this system, say 1 over s, I would get not just a bounded output of 1, but I would get a bounded output of 0. And so this s, this 0 in the numerator has some kind of special properties. And it's really, if you think about it, a derivative of the input that we're looking at. and hence why we're getting, even though this is increasing linearly, this derivative in the input on the plant is, if this is a constantly increasing system, then it's just now like a constant going into the system. So finally, we can look at one last example where we have a bounded input and we have an unbounded output. And really what this is saying is we have an unstable system. So if we let's use the position transfer function of the DC motor. That's K over S tau S plus 1. So again, this is marginally stable or neutrally stable because I have a pole at 0 and minus 1 over tau, and if tau is positive, then this pole is stable, but this pole is on the j omega axis, so we would say this is marginally stable. So again, if we look at the limit of S times H of S times U of S, and sorry, I should say let's let U of S equal 1 over S, so we have a bounded input as S goes to 0. That's the limit of, as S going to 0, of S times K over S tau S plus 1 times 1 over S. Those S's cancel. And notice this S in the denominator here causes this limit to go to infinity. And again, not quite proper use of the final value theorem. So we can look at the time domain solution, and we find that from using MATLAB that y of t ends up being kt minus k tau plus k tau e to the minus t over tau. Well, this looks oddly familiar, right? This is the same kind of situation where we had the speed being driven by a ramp, but here we have the position being driven by a constant, and we get the same kind of solution. And so we do see that this goes to infinity as t goes to infinity. But again, this makes sense because this system is marginally stable, and if you drive it with a constant voltage, so it's a motor, you put a constant voltage into it, the position of the shaft of the motor, the angular position, will just increase linearly over time, right? So if I have, here's t, and here's, say, the input, u of t, then for this system we know that the output, y, or it's really theta m of t, will just increase linearly. So it's an unstable system. So BIUBO. So there are a number of cases here that we've looked at. We have the bounded input, bounded output stable system. We have an unbounded input, unbounded output, but a stable system. We have an unbounded input, bounded output example where we have the system is stable, right? It has poles that are have negative real part, but it has this 0, which has this kind of canceling effect of one of the integrators of the input. And then we have a case where we have a bounded input, unbounded output, where we have an unstable example. So really, from all of this, the takeaway is that the only time that you can really make a judgment about the stability of the system is when you have a bounded input, bounded output, or if you have unbounded input, bounded output. The unbounded input, unbounded output doesn't really tell us about stability, and the bounded input, unbounded output is problematic because of the application of the final value theorem. We really have to look at the time domain solution, and there are cases when we could have bounded input, unbounded output, even though we have a stable system.